Bismillahirrahmanirrahim. Assalamu alaikum. So in this small session, we will be talking about a bounding theorem related to complex integration, a bounding theorem. Don't forget that this theorem is also called also known as an ML inequality, right? So inequality, right? Let's state this theorem. So it says that if we have a function which is of course complex valued, if f is continuous, on a smooth curve, c. So we have a function which is continuous on a smooth curve and it is bounded, and f of z has modulus which is bounded by m, or f of z has the modulus less than equal to an m. So of course this m is going to be a non-negative real number for all z in the complex z on c. Okay, so on on curve. Then it says that then we have this inequality over here, which is the integral of f of z with respect to z over the curve. Its absolute value or modulus is bounded by ml, where where L is the length of the curve, so length of the curve. But in the case of circle, it is going to be circumference. So in the case of ellipse, it is also going to be somehow the circumference, but in the case of line segment, it is going to be the length, right? So it's basically, if I give you the rough idea, so it says that if you want to integrate this, uh, then what we already know, that the integral over c of this f has absolute value bounded by this. So this inequality is famous from our literature, and we know that this f of z is bounded by m. So this is going to be less than equal to the integral of m over the curve c, which can be written as m times the uh, integral of 1 over the curve, which is of course the length of the curve. So this is a rough kind of sketch to the proof, but not it's really not an abstract one, because it requires summation and all of those things. One can prove using the definition of this contour integral, or this complex integral, in the sense of summation, where we partition the interval. The good news is you can use this ML inequality, or bounding theorem, to find out bound on certain integrals. For example, we have got this integral of e to the z over z plus 1 with respect to z. So I want to find out bound on this interval, the upper bound on this interval, where my c is a circle of radius 4 centered at origin. So I just need to compute m from this f of z. So for this f of z, what I have to do is basically I have to compute m. And what is going to be the L? So the L is going to be the circumference of the circle, which has the radius 2, of course, radius 2. So the circumference is 2 pi r, where r is the radius. So when you substitute the value of r over here, sorry, so the radius is 4, yes, not 2, because this means that square root of x square plus y square is 4. So that means x square plus y square is 16. So you can say that the radius is 4. So it is going to be 8 pi. So L is 8 pi. I only need to compute my m. Okay. So I will, play with certain inequalities, which I will state now. Notice you can verify that. So you can verify that the absolute of z plus 1 is greater than equal to absolute of z minus 1, and and the absolute of z in our case is equal to 4, so it is 4 minus 1, which is 3. So you can say that the 3 is less than equal to absolute of z plus 1, and of course this is not negative, and you can conclude from here 3 over absolute of z plus 1 is of course less than equal to 1. And then what can you do? Basically, you can also write from here 1 over absolute of z plus 1 has the value less than equal to 1 over 3. So when you multiply both sides the absolute of e to the z, so you will have absolute of or modulus of e to the z divided by modulus of z plus 1 to be less than equal to e to the z divided by 3. And so like e to the z is uh, you can see one thing. Now I'll work with this absolute of e to the z. So e to the z can be written as e to the x plus iy, and then it can be written as absolute of e to the x times the absolute of cos y plus iota sine y, right? And you can see that this has absolute value 1. So of course cos square plus sine square has 1, so this is equal to absolute of e to the x. But on the circle, when you draw this, so like the absolute of e to the z is totally depending on the e to the x. So x, when I say e to the x as a function and one variable, so it is increasing function. So what is the maximum value of x that x can take? So this is circle, and x can take either minimum value -4 and maximum value 4. So like it is increasing function, so at x to be 4, this should have the maximum value, or another word I can say that this is less than equal to e to the 4, right? So by combining this with this, I can say that absolute of e to the z divided by z plus 1, this should be less than equal to e to the 4 over 3. So this will be kind of m of mine. So this is my m, right? Because I can write this e to the z over absolute of z, so z plus 1 of course, and its absolute can be written as less than equal to e to the 4 over 3. So this is m. Now I have m, I also have l. So using ml inequality, I can say that the upper bound for this integral is going to be equal to should be less than equal to m times l, and this my r1 can say that this integral has upper bound less than equal to so like less than equal to the value of m is e to the 4 over 3, and the value of l is 8 pi. So you can say that this integral can be bounded by 8 pi e to the 4 over 3. So this was an application of an ML inequality, or the so-called bounding theorem. In the next videos, we will be talking about Cauchy Goursat theorem and much more about the complex integration. Stay connected. Don't forget to subscribe, like, and share with your friends. And we will be waiting for your kind suggestions in our comment section. Thank you.